Hey, welcome to what will be new chapter, section 2. In this one, we're going to talk about the division properties of exponents. So we talked about multiplication in the past. Today, we're going to talk more about division properties, look at our powers, and compare a bunch of things that are going on to help us understand what these things mean. So in the past, we multiplied our terms. We used the word monomial. And now we're going to practice finding the quotient, which is a word which means division, between two different terms. We'll use the word monomial again. We can simplify our expressions that contain negative exponents as well as zero exponents. It is when you have a exponent to the zero power. So we'll look at all those things going forward. Zeros and negatives, this phrase order of magnitude, which just means how many powers of 10 are there as we get going. So here's the first rule we want to talk about, and that is the quotient of powers. So when you're dividing a power by another power, and they have the same base, you simply subtract the powers. So base a to the power m and the same base to the power p is the same thing as a to the power of m minus p, which you see here. So one example of that, c to the 11th divided by c to the 8th is the same thing as c to the 11 minus 8, or c to the 3rd, because 11 minus 8 is 3. By the same logic, r to the 5th and r squared, if you divide those, you get the difference between the powers, that is r cubed. So that rule can help us solve a couple problems like this. Given this division, we want to simplify the powers and write this as the simplest form possible. We can also assume that x and y are not equal to 0 because we never can divide by 0 in math. And you see those in the denominator. So first, we can group our powers that have the same base. So if we group our x's together, it looks like this. We can group our y's together that we started with, it'll look like that. And if we do our division, we're going to subtract our powers. So 7 minus 6 is going to give us x to the 1st. And 12 minus 3 should give us y to the 9th. So that will look like this. Quotient of powers tells us to subtract the powers of the same base. Subtract the powers of the same base. And we all can do 7 minus 6, that's 1. And 12 minus 3 is 9. So we get x to the 1, or just x, and y to the 9th. And that is as simple as it gets. So this whole phrase that we started with is the same thing as x times y to the 9th power. And that is our answer for 1a. Using that first rule, when we have the same base and we divide, we can subtract the difference of the powers. X times y to the 9th for 1a. Now 1b is going to give us a similar type problem. We're going to use that same rule. So if we have the same base, we can subtract the powers. Of course, we again assume that the denominator is not 0. So we have a to the 3rd over a. Let's first group all these things by common bases. So we have a to the 3rd over 1a. And then we also have our b's. So we have b to the 9th over b squared. So if all of that is true, we can now go ahead and subtract our powers. So if we have 3, and this is to the power of 1, we don't normally write it, but a variable is just to the power of 1 if there's nothing there. So this is the same thing as a to the 3 minus 1. So this is the same thing as a to the power of 3 minus 1. And that's times the quantity, b to the power of 9 minus 2, because those powers are being divided there. 9 take away 2. Now from this step, to get to our final step to get our answer, we simply just subtract the powers. So a to the 3 minus 1 is the same thing as a squared. B to the 9 minus 2 is the same thing as b to the 7th. So we get a squared b to the 7th. Now we look at our options. We know it must be letter choice D, given these rules. Same basis, subtract the powers, get your answer. So D, a squared b7 on 1b. Double check to confirm, it looks like that. That is true. Okay, so we're making things more complicated. Now we want to look at the power of a quotient. So given one number divided by another number, or a over b. If all of that is taken to some power, m, we must apply that power to both numerator and denominator. So example, if we have 3/5 as a fraction taken to the fourth power, that fourth power must go to the numerator and the denominator. So this would look like that. If we had just variables, say r over t, all to the fifth, that's the same thing as r to the fifth over t to the fifth. So the rule tells us apply your power to both top and bottom. So let's look at an example of that. So given this whole expression here for 2a, you want to start writing that down. We have the third power that we're applying to everything. So the third power will apply to everything in the numerator and everything in the denominator. So the first step will be to rewrite that and break it down. Make sure we apply that power of 3 to everything. So first, apply the power everywhere. That'll look like this. Notice the 3 on the outside of everything on top and on the bottom. Now you're going to have to rewrite what you can and simplify. So we have 4 to the third, we have c3 to the third, and d2 to the third, and then we have 5 cubed on the bottom. So simplify what we can. So now we've applied the 3 to everything on top, each term, and on the bottom. 4 cubed is just a number, 5 cubed is just a number. And we do the power of a power here, we're going to multiply. So c cubed to the third is going to be c to the 3 times 3, which should be c to the ninth. Here we have d squared to the third. So power of a power, we're going to multiply. So that's d to the sixth up there. So all of those will look like this. So 4 cubed became a 64. C to the third became 3 times 3, which is 9 for the power of c. And d squared to the third became 2 times 3, which is 6 here. 5 cubed is 125. So all of that in simplest form looks like that. And that is our perfect answer for the power of a quotient on 2a. And we can double check that. Looks like that. Use your power, apply it to everything, and then simplify. 64, c to the ninth, d to the sixth, all over 125. Now here is 2b. We're going to use the same process to solve this one. So we see the power of 3 on the outside of our whole sequence here. So we're going to apply that to everything. We're told, assume the denominator is not 0, so we know that's happening as well. So first I'm going to rewrite this and apply my cube to everything. So we have 3, the number 3 cubed. We have m to the third. All of that will be cubed. We have n squared, which will also be cubed. So we're cubing every term here. Then on the bottom we'll have 4 cubed, p to the fifth cubed, and q cubed. So we applied the 3 to everything in our equation here. If you see from here to here, that's what we did. There's a 3 power added to everything. Now we can simplify what is here. So 3 to the third, I know is the number, that's 27. M to the third is going to be 3 times 3 for the power of m. So that is m to the ninth. The power of a power, we always multiply. So n squared to the third is going to be n to the 2 times 3, which is n to the sixth. Looks like that. So we're done on top. On the bottom, we get 4 cubed. So 4 times 4 times 4 is 64. P to the 5 times 3 is going to be p to the 15th. And then one more q cubed is just q cubed. Can't do anything with that, so just leave that as is. Now the question is everything in simplest form? And it looks like it is to me. So if we double check and confirm, our solution is letter choice B. So none of the other ones make sense there because they didn't have the right terms or the right powers. So 27, 64, we have n to the 9, n to the 6th, p to the 15th, q to the 3rd. All of that is done perfectly using our distribution of that 3 power to every term in our sequence, top and bottom. If you do that, you'll get what you need on these kind of problems. No, it goes to every term, top and bottom. So this example, letter choice B. Great. So now with those rules aside, we have a couple more to think about. This one's pretty easy. So anything to the 0 power is going to be equal to the value of 1. Very easy rule. So a, any value taken to the 0 power is equal to 1. So say you have 15 to the 0, that's 1. Say you have some number over another number to the 0, that's also 1. And say, for just the sake of an example, if you had 2 over 7 to the 0, that's also 1. So anything at all, anything to the 0 power is 1. So let's think about it. Say we have this example, we want to simplify it, assume our denominator is not 0. So we have all of this mess going on inside of here, but it's all taken to the 0 power. So no matter how complex all of this is, if it is all taken to the 0 power, no matter what it is that's in there, the answer will still be 1. And that is it. That is all we have to say. Because anything to the 0 power is just that simple value of 1. So in 3a, you can write that whole phrase, but we know anything at all to the 0 power makes our life very simple. We can just say that is the value of 1. Okay, with that in mind, let's try 3b. Now this one's easy, but it's not as easy as that last one. We got to use the rule we just talked about and then simplify what we can. So we'll assume the denominator is not 0, and we see we have m to the 0 power. So m to the 0 power, this term itself, only that term, is equal to 1. So let's rewrite that. M to the 0 is 1, so we rewrite that here. Leave everything else as is. Now if we have 1 times some term, 1 times that is just itself, so we can think the numerator is just n cubed. So if we have n cubed over n squared, can we rewrite that? Well, the answer is yes. Cubed over squared with the same base is the same thing as n to the power of 3 minus 2. And we know 3 minus 2 is just 1. So what is another way to say this same phrase? Well, n to the third, or n cubed, over n squared is just n. N to the first is just n, using our quotient of powers rule. So this phrase that we started with is the same thing as just saying n. And that's it. So 3b, our answer is just n. Using our rule, same basis, when we divide, we subtract the powers, and we get just n. We also knew m to the 0 was just 1, so that all disappeared. And we're left with this nice, neat, easy answer for 3b. Great, so one more rule to talk about, and this one is with a negative exponent. So basically what you need to know is anytime there's a negative exponent, you need to move your value, you move your base to the other side of your fraction, and then that makes your power positive. So example, if we had some numbers with a negative in power, put it as 1 over that whole thing, and then your power becomes positive. So say you had 2 to the negative fourth, that's the same thing as 1 over 2 to the fourth. So you just flip it, put it on the bottom, your power becomes positive. It just so happens that 2 to the fourth is also 16, so you could write this also as 1/16. The point is, anytime you have a negative power, to make it positive, you put it on the other side of the fraction. So say you have 1 over j to the negative fourth. To make your exponent positive, you must put it on top. So that would be j to the fourth over 1, or just j to the fourth. So whenever your exponent is negative, you put it on the other side of the fraction. And that makes it positive. So it works going down or going up, either way. So let's use that rule to solve a couple problems. In this one, we're given this phrase to start. We can assume our denominator is not equal to 0. And we have negative exponents, so we need to move these things around. So where we have an x to the negative 4, we need to move that to the bottom. That'll make it positive. Here we have a z to the negative 6. We got to move that up top. That'll make this 6 positive. So we can do both of those things. So from here to here, look at what changed. We moved what had a negative power to the opposite side of our fraction, and it made the power the other side. So I'm going to circle these things and put the same color around them so we can see. But we see here and here, We moved both of these things around and it made our powers positive. And this is the way our answers need to be written. So you'll never want to solve a problem that has a negative exponent in it. You don't want to leave that as your answer. You always want to make it have a positive exponent. So even though we were given this, the simpler way to say that looks like this. All positive exponents. Now, since we have a y, a z, and an x, all those are different terms. So we can't actually simplify it any more than that. So using our negative exponent property, that is as simple as this problem gets. We flip it. What's on the bottom goes up top, makes it positive. What's on top goes to the bottom, makes that positive. And we're done with simplifying on that one. So for A, your answer is y to the 9th, z to the 6th, all over x to the 4th. Great. So with that in mind, we can do one a little bit more complex. We'll assume again our denominator is not 0 and simplify what we can. So everywhere there is a negative value, we need to move those things around. One strategy you can use to try to simplify it, you see here, is to group your powers with the same base. So that means group everything together. So where you have constants, let's group those together. So our numbers, 75 and 15. Where we have the variable p, let's group those together. So you see the 3 and the 5. Take it from here. We can group our q's together, looks like that. And we have an r to the negative 8 by itself. There's no r on top, so you can just put a 1. Now after you group it, you can simplify each one of these and then bring them back together. So you can think about 75 over 15 is just going to give us a number. P to the 3rd over P to the 5th. If you divide, you subtract your powers. So you can think about as you subtract what you would get. So if you rewrite each one of these as a subtraction problem, here we get 5, the number. Here you get P to the 3 minus 5, looks like this. Here we get Q to the negative 5 minus a negative 4 if we keep track of all of our signs. Subtracting, and we still have a negative, so minus a negative 4. And then here we just have r to the 8th power. Because if this is in the bottom, we can move it up top and then make it positive. So this is the same thing as r to the 8th. Now we can simplify these subtraction signs and get a little bit closer. So we know 3 minus 5 is negative 2 for P. And negative 5 plus 4 is a negative 1. So that will look like this. So we went from this phrase. We simplify the P, we get a negative 2 here. Simplify the Q power, we get a negative 1 here. So all of that looks like this. And from here, we can simplify again. So we have negative power. So everywhere there's a negative power, those will become denominator terms. And our variable then will become a positive power. So P to the negative 2 will become divided by P squared. Q to the negative 1 will be divided by Q. So everything that's a negative, bring it down and write that as a denominator. It would look like that. Now we can rewrite this so everything that is just a term being multiplied will be on top. Our dividing terms that we just changed our signs will be on the bottom. So if we rewrite that, we'll get 5 r to the 8th, all divided by p squared q. And that's just using our negative exponent property. So that will look like this. 5 times r to the 8th, all divided by p squared q. Now that is our final answer for this example 4 type problem. So the goal is to use these rules we talked about for all of our exponents to solve these problems. So if you have something to the 0 power, you need to make it just the value of 1. A negative exponent, you need to flip your term. And if you divide with the same base, you need to subtract with our quotients. You need to subtract for your exponents. So we use all those rules to solve our problems today as we progress.